Hello, this is microcontrollers. On this video, we're going to present our project, which consists in making an arithmetic logic unit using the microcontroller of PIC18F4550. Our team is conformed by Steven Sebastián, Jairo Said, and Francisco Mendoza. On this part, we can see the header files and the configuration bits. After that, we are located on variables definition, and we declare three equals named input, data A, and data B. We also declare 16 constants that are going to represent our 16 operations. And then on initialize, we declare the port B as an input, the port D as an output, the pins of port D, of port A, RA1, RA0, and RA2 as inputs, and the pins of port E, RE0, RE1, and RE2 as outputs. Then in the main, we call initialize, and we are going to test our stimulus or pins of inputs, and depends on the value which contains, it's the operation that is going to execute. If we push the pin RA0, we are going to go to the weight 1. We have to push it again to go to operation 1, that it is going to put the value of port B on data A. Then we go back to loop, and now we press the pin of R1, RA1, and we're going to move to the weight number 2, and we have to push again the RA1 pin to go to the operation number 2, and this operation is going to put the value of port B on the data B value, on the data B. And then we go back to loop, and we push the RA2 button. We go to operation weight 3, and we have to push it again to go to operation number 3.
In operation number 3, we can see how, depending on the input value of RB0 to RB7, we can select the type of operation we want the arithmetic logic unit to perform. It checks the input value and puts it in the accumulator. Afterwards, it subtracts an already defined value in the constants. If the result is 0, then the program jumps to the specified destination and performs the operation. When we select the value 1 in the pin RB1, we jump to the operation output 1. In here, we have a subtraction operation. We have the data B and data A. The data B is going to be moved to the accumulator. Afterwards, we upload the data A, and in the sub WF instruction, we say that we want data A minus data B. The result is going to be uploaded to the accumulator. Then, from the accumulator, it is going to be uploaded to the port D. Finally, in every single operation, it goes to the label update. Afterwards, we have the decrement operation. In the decrement, we have data A be uploaded to the accumulator, and then it is decremented by 1 unit. In the output 3, we have the increment operation, where data A is uploaded to the accumulator and incremented 1 unit. In output 4, we have the AND operation, where data A is uploaded to the accumulator and then is run through an AND operation with the data B. In the output 5, we have an OR operation, where again, the data A is uploaded to the accumulator and run through an OR operation. In the output 6, we have an XOR operation. In the output 7, we have a complement, where we take the data A and swap all the zeros to 1 and vice versa. We have the output 8 be set F, where all the pins are set to 1. We have output 9, which is clear F, where all the pins are set to 0. Then we have the output 10, which moves the data A to the port D. In output 11, we have a multiplication between data A and data B. In output 12, we have an A2's complement for data A. The output 13, we have an RLCF operation with data A, which basically shifts all the pins to the left and adds the carry bit. In output 14, we have the swap operation, which swaps all the nibbles. And finally, in output 15, we have the RRCF operation, which shifts all the pins to the right and adds the carry bit.
As you can see, after any of the 16 arithmetic operation is executed, the program goes to the label update. In this subroutine, we basically update the port E with the flags of status register. This means the carry flag, the 0 flag, and the negative flag. How do we do this? Well, first we just prove with the instruction BC if the carry flag is 1. If it is 1, then the program jumps to the label update RE0, where we basically move the value of 1 to the accumulator, and then we move it to the pin RE0 of the port E. In case that the carry flag is not 1, so this means it's 0, the program would just go to the next line, which is where we move the value of 0 to the accumulator, and then we charge it on RE0 pin of the port E. After any of these two instructions is executed, the program then jumps to the label update RE1 1. It doesn't matter if the carry flag was 0 or 1, the program will jump anyways to the next label. And here we do basically the same. We just prove, in this case, if the 0 flag is 1. So if it's 1, then we charge the value of 1 to RE1. And if the 0 flag is 0, then we charge the value of 0 to RE1. And the same thing, after executing any of these two instructions, the program jumps to the next label, which is update RE2 1, where we do the same, but now with the negative flag. Here we just prove if the negative flag is 1, and if it's 1, then we charge the value of 1 on RE2, and if it's 0, then we charge the value of 0 on RE2. So we are basically updating the pins RE0, RE1, and RE2 with the values of the flags, of the 0, the carry flag, the 0 flag, and the negative flag. So now we're going to show you if our program works because that's the main goal of this project. So I'm going to clean and build. So as you can see, it's totally clean, and then we are going to debug, and we are going to show how we execute the program to make 3 different arithmetic operations. we're going to make a multiplication, an A2 complement, and a swap operation. Okay, so now we're going to realize, well, to make an A2 complement operation. This operation basically just gives us the negative of the number you put in input. This means if you, for example, test the A2 complement for the value of 10, then the answer is going to be minus 10. If the input is 5, the answer is going to be minus 5. So basically the A2 complement just negates the number. So we are now in debugging. We have the watches and the same stimulus as before, so we're just going to step into where until we declare the ports as inputs and outputs as we talked before. So yeah, in order to make the A2 complement, we have to give data a value. So I'm just gonna give it the value of 10, for example. So I have to give, well, first of all, I have to choose that I want to go to the first operation where we are going to give the value to the data A. So I have to press the stimulus A0. When I do this, then as you can see, we will go to the go to wait 1 subroutine. Here we have to press the RA0 button again so we can jump to the operation number 1. So I'm going to do it. And as you can see, now we will go to the operation number 1. So in operation number 1, we're going to move the value of the port B to the accumulator and then to the data A. So this means I have to give the port B the value of 10. So I have the 8 pins of port B here, so the value of 10 would be, I think, 8 plus 2. Anyways, we have the watches to see if I put the correct value. And yeah, as you can see, here the port B is equal to 10. So we're going to move the value of 10 to the accumulator. As you can see, it's moved to the accumulator, and then it's moved to data A. So now we just charge the data A with a value of 10. So we're going back to the loop, and then we just have to press now the pin RA2 to go to the operation number 3, so we can select the arithmetic operation that we want to execute. So I have to press RB2. So this will send me to the subroutine wait 3. Oh no, it was not RB2. Sorry, it was RA2. So this will send me to the subroutine wait 3, where I have to press again RA2, so we can jump to the operation number 3. So I'm just going to do it. And as you can see, then we just go to the operation number 3. But before jumping to the operation number 3, we have to find where the 8 complement is located. And as you can see, it's on the output number 12. So I have to give the port B the value of 12, so we can choose the arithmetic operation which is located in the output 12. So I'm going to use a stimulus to give the port B the number 12. Right now, as you can see, it's 10, so I just need to add 2, but I think I have to press again RB3 and RB1. So this makes it 0, so 8 plus 4. I guess that's it. Now the port B should be 12. Let's see. Stepping into. Yeah, as you can see, the port B now is 12. So we're just going to find the location of the output number 12 by pressing step into, and it should work. Let's see. So here it is. We should jump to the output 12. So yeah, there it is. So now we are on the output 12 where we are going to execute the A2 complement operation. So as I told you before, we are basically going to negate the data A value. So right now the data A is 10, as I told you before. So the instruction negF is just going to negate the data A and save it. So as you can see, data A was negated, and now we move it to the accumulator, and then it's moved to the port D. And as you can see, the port D is now charged with the negative number of data A, which is minus 10, but this decimal numeration is just shows you the opposite counting. If we go to the status register, we will find out that the negative flag is now activated because we have a negative number in the result. So now we just need to go to the update subroutine, where we are going to update the port E with the flags of status register. So now, since the carry flag is 0, we're just going to move the value of 0 to RE0. These two lines just made it. So as you can see now, RE0 is 0 because we just moved the value to that pin. So now we go to the next subroutine where we move the value of the 0 flag. Well, we proved the 0 flag is 0, which is CD 0, so it's just going to jump and move the value of 0 to RE1, and there it is. As you can see, RE1 is now 0, as well as RE0, and then we just jump to the next subroutine, which will just prove if the negative flag is 1. And since the negative flag, as you can see, is 1, then the program will automatically jump to the other subroutine where we move the value of 1 to the accumulator, and then we move it to RE2. And as you can see now, we just basically uploaded the values of the carry flag, the 0 flag, and the negative flag to the pins RE0, RE1, and RE2 of the port E.
Multiplication is performed between the values of data A and data B. In this part, we go to main and we call initialize. We declare all the ports as we mentioned before, and in this part of the loop, we have to test if the pin RA0 is 1. As now is 1, and he's going to jump to the instruction wait 1, and is going to stay in there until we push RA0 again. Now that we have pushed the button, is going to jump to the operation number 1, that is this operation is going to move the value that is in port B to the data A using the accumulator. And it's going back to the loop with the value of 6. Now we have to push RA1, and it is going to jump to the wait to instruction. Here is going to stay until we push RA1 again, and it is going to jump to the operation number 2. And this operation is going to put the value that is in port B and moves to the data B using the accumulator. And now we have to push A2 using stimulus, and it is going to jump to the instruction wait 3, and it is going to stay until we push it again. Now we have pushed, it is going to the operation number 3.
Now, before going to the operation number 3, we have to locate where the multiplication operation is located. So if we go down in our code, we will see that the operation of product and multiplication, it's located in the output number 11. So this means I have to use the stimulus to give the port B the value of 11 so it can find this location. So right now the port B has a value of 2. So if I want to give it the value of 11, I have to press this stimulus, which is 8 plus 2 plus 1. This stimulus is 1. So right now it should be 11. Let's see if I'm correct. Yeah, as you can see right now port B is 11. So this means the program will find, or well, will step into until it finds the output number 11. So just let me step into, and here it is. The program should jump to the output number 11. And yes, there it is. So right now, as I told you, we're going to realize, or well, to execute the operation of the multiplication of data A times data B. So as you can see, data A has a value of 6, and data B has a value of 2. So this means the result should be 12. So first we're going to move the value of data A to the accumulator, which is 6. So we press step into, and as you can see, the accumulator now has the value of 6. Now we execute the operation mul WF, which will multiply the value on data B times the value on the accumulator, which is 6, which is the value of data A. So this means 6 times 2. So when we do this, the result is stored in the SFR called prot_l. So as you can see here, the result of the multiplication of 6 times 2 is 12. This number was stored in this SFR. So now we are going to move it from the prot_l SFR to the accumulator, as you can see, and then we're going to move it from the accumulator to the port D. And there it is. Finally, what the PBL asks us to do is to move the result to the port D. And as you can see, there it is, the number 12. And then after finishing the operation successfully, we're going to jump to the label update to update the flags of the status register on the port E. So let's see what the flags are. As you can see, when we open the status pins, we can see that the carry flag is now 1, the negative flag is 0, and the 0 flag is 0, 2. So I'm just gonna press step into to assure the video. I'm just gonna do it quickly, and in the end you will see that now RE0 has a value of 1, RE1 has a value of 0, and RE2 has the value of 0.
So in this example, we're going to see the swap operation. First of all, we have to define every single constant. Now I'm going to give my data a value. So I'm going with 1, 1, 1. We activated our RA0 to go to the wait 1. Now we deactivate it. And in this operation, we're going to have the value we input in port B be saved to the data A register. Now for the swap operation, we have to go to the instruction 14. So I'm going to put 14 in binary and activate array2. I'm going to deactivate it now. And it's going to check if the operation, or if the subtraction operation is equal to 0. Then it knows which operation we want the program to execute. As we can see, we already reached 14. Now, if we see the data in data A, it is 0001, 0011. After the swap operation, all the nibbles will be swapped. So the first 4 digits will be the last 4 digits and vice versa. And it's going to be saved to the accumulator. So if we check the accumulator, as expected, now it's 0011, 0001. Afterwards, it goes to the update subroutine, and it's going to check in the status if the bit carry is 1, and if the bit 0 is 1, and if the negative bit is 1. Because the bit carry is 1, it's going to upload a value of 0, 1 to RE0. And also because the bit 0 is 1, it is also going to upload a value of 0, 1 to RE1. Because the negative bit is 0, and the program will run as expected. And this is the end of the instruction.